So what I would want to speak to you about is this passion that's really been my passion throughout my career, which is, well, let me say I have two passions. One is the passion to figure out how AI and intelligence works. That's sort of the fundamental science. But at the same time, I've always wanted to make a contribution with the basic research that we do and see that we can help the world in a positive way. And so one of the main thrust of our research at our lab has always been to overcome language barriers and communication barriers between people. And as you look at these problems with communication, you quickly realize that communication is very, very complex. It is not just text. People think that all we need to do is translate text between languages. But as we will hopefully develop in this talk, it is much more. And in fact, every one of these layers has its own complexities. So let me just jump right in and see what we mean by that and how we develop technologies to do that. So it's really from initially machine translation all the way to language or communication barriers, overcoming those barriers. I hope you can see my slides.
Yes.
So there are, of course, references which I can share. I don't expect you to copy them now, but I'd like to start off by thanking a generation of students, probably close to 100 PhD students by now, who have really labored passionately and also laboriously on many of these aspects. So much of the credit goes to them for their patience and their hard work that made many of these contributions possible. So the problem that we like to address is again, these language problems, the communication problems. And as you all know, there are 7,000 plus languages in this world. And the question is, how do we actually communicate when there are so many languages? It's a much harder problem than just, for example, face recognition. Somebody asked me that question because we have language is compositional, and every language composes phonemes and sounds and whatnot in different ways. And there are 7,000 languages and dialects and so on. And doing this in every possible languages seems close to impossible. It's also impossible for humans to do this task of translation. We have worked for a while, and I will show you pictures with the European Parliament. It's a remarkable task. It's very difficult to do language communication and interpretation. And as a result, it also needs technical solutions if we really want to overcome barriers so that everyone around the planet can understand each other. But we don't want to stop there, because it's as soon as we start talking about how can we remove the communication barriers, we immediately realize that it really depends on the setup. If you have a phone and you're talking with someone else facing that person, you have a different setup. You have a device that has to be local. It has to be small. It has to be between people without disturbing the communication. If you're in a conversation in a meeting, then again, you want to face different people who may speak different languages. There you have, again, different situations, both in terms of acoustics, in terms of facing multiple people, multi-talkers, and then the devices and hardware situations. If you're giving a lecture, it's yet another situation where you're not carrying out a dialogue. It's mostly a monologue where some person keeps on talking for a while, and you want to get in real time at low latency the interpretation of that. So these were challenges that became apparent as we went on throughout the years that we worked on this, and gradually we addressed many of them, and I'd like to walk you through some of them. Now, again, first of all, we need to realize that language is not just text. We have social media, we have signs, we have images, we have spoken language. It's this fluent and noisy. We have meta information, emotion, language IDs, style, speaker, formality. All of those contribute to the way we communicate, and they vary quite a bit based on the setup. Translation, therefore, has to be somehow as a mediator. It has to mediate between two people and explore really what the intent is of what one person wants to communicate to another. And that's, again, as I said, not just done by translating the words. Now, we have throughout this, let me walk you through perhaps a bit of the history of all of this. We started in the early 90s. As I said, my work on neural networks started in the 80s. But in the 90s, we were in a position where we could build a first speech translation system where we could use speech and translate it to another language. Now, it was limited vocabulary. It wouldn't do really much, 500 words, and you had to speak syntactically correct. So it was a bit of a problem not to do this in real time at arbitrary vocabularies. And so it took, again, more time to move to spontaneous speech, because spontaneous speech is, again, very different from read speech or from well-formulated speech because of fluencies and so on. And then more time, again, to do this in unlimited domain, unlimited text, so we can speak anything we want. And now to take all of this and bring it again to deployable systems was yet another decade almost to get that done, to go to wearable devices, broadcast speech, lectures, European Parliament, and finally transfer this into industry so that it becomes commercial products. And then last not least, I'd like at the end of the talk give you an idea of what we're doing now with respect to language transparence, which I view as the next generation of these devices so that it becomes even more natural. And what do we mean by natural language transparence? A bit to, as a spoiler alert, what we mean by this is when we translate, it becomes translation of text, let's say, but it's not necessarily helping us in the communication if it intervenes or interferes with the human-to-human interaction. We'd like to be at the end of all of our research in a position where you have a communication that is interrupted by culture, by language, by distance, etc. And we want to be in a position where we can relay what people have to say or communicate to each other in a way that you don't even notice anymore that there is a barrier. Again, if you have something that intervenes or interrupts speakers, that is suboptimal. And I will show you some of that. So initial systems, again, where the first you start with speech translation. Machine translation has, of course, been a dream in AI for many years. In fact, the entire field of computer science was probably initiated by machine translation or by the desire to translate. In the Second World War, people tried to translate between Russian and other languages and English. And they decided that it was too hard to do machine translation. But it gave rise to, for example, information theory and many other fields that would gradually consider the translation problem as a noisy channel, and that led to later on the statistical approaches. So machine translation by itself was difficult, but people tinkered with it already as far back as the 60s and 50s and so on, with little success. In the 70s, when I got interested in this vision, people thought I was crazy because, I was, of course, still a student at the time and didn't understand that machine translation was hard and that speech recognition was hard, and combining all of these things seemed close to impossible. Nevertheless, we got started, and you need a device like this where you convert speech into text first, and then you translate text from one language to another, and then you want to synthesize it and make it audible by the other side, by someone on the other end, and then you want to do this all in reverse to create a dialogue between two people. Now, how do you do this? First of all, we need always at least two technologies, maybe more. One is this conversion of speech into text, and then the conversion from text in one language to another, machine translation. So if we approach this in the 90s, again, people didn't know what to do with recognition. People didn't know what to do with translation. And at the time, due to computing limitations, we set out to do work on speech recognition with neural networks in the late 80s already. Again, I'll say a word later about this. Not everyone believed this was possible. And we worked on translation elements with knowledge-based approaches, grammar-based approaches to translate from one language to the other. Now, because it required grammars, in those days it was then domain limited. We could only do translation, speech translation for certain domains like conference registration or medical, etc. Time went by, and we then gradually switched to statistical approaches because we could apply machine learning. So we could eliminate, at least in the machine translation, with statistical machine translation, we could gradually eliminate the hand design of grammar rules and thereby expand to larger domains. And when that happened, we could then go to domain unlimited speech translation. And that was very exciting to see, and you'll see some of the results from that. Then in the 2016, finally, neural networks came into the fore again, I should say, because now we had the computing power that we could build larger systems, both in speech and eventually in machine translation. And we'll see enormous progress was made. And then the movement towards transformer, yet more progress and improvements. And the current debate, of course, that preoccupies us now is end-to-end or cascaded systems where we remove potentially the boundary between speech and MT altogether. Is that perhaps better than a cascaded approach, or should eventually people move to large language models? And I will say a little bit about that as well. The basic lesson, though, always is improvements came with less engineering and more data and machine learning. So as soon as we eliminated some of the hand design and we allowed a machine learning system to do its things based on a suitable learning model and a sufficient amount of data, then we would achieve some amount of success. Now, why was it that in the 1980s, I should say, there was, let's say, in a problem like machine translation, speech recognition, it was unthinkable of, or people didn't know how to approach these different things. And there were many competing approaches. There was knowledge-based, statistical, neural, and so on. I became immediately excited about neural networks when I was introduced. In my PhD thesis, I already worked with perceptrons. And when I learned about this new algorithm backpropagation in the 80s, I was immediately taken and thought, why? For two reasons. One is a neural network did not require, it could first of all be a nonlinear classifier, but there were other possibilities to do nonlinear classifiers. But another two aspects that only such large neural networks or neural networks could do for us is that they were agnostic as to what features you feed them. So you could just put visual features, acoustic features, text features. It doesn't really matter. The neural network would figure it out and learn from it. So that was one big plus, because again, if we're interested in communication, we don't want to be limited to one modality only. The other thing that was exciting and led to lots of debate at the time was that a neural network, when you learn it, learns hidden representations. It learns representations inside as abstractions of a particular task, and that's world knowledge that you can redeploy and reuse. And that became clear to me was just an absolutely winning, essential aspect of that in the 80s. And as we now know, it is in fact the most crucial aspect of modern AI, because as you're learning large hidden representations, you can effectively absorb the knowledge of the world and apply it in very exciting and interesting ways. And in the late 80s, though, we had one problem that if you want to do classification without segmentation, you needed shift invariance. And so we came up with this TDNN, which later got renamed by our vision colleagues as convolutional neural networks, because we can then do shift invariance both in time as well as in XY if you want to do image classification. So the TDNN gave us a possibility of taking it then to speech recognition of continuous speech, and remained a successful model up to this day. We still use TDNN convolutional approaches for various applications. So we could show in those days already in the 80s that shift invariance was possible. It would classify independent of shift. We could also do transfer learning. We could take the hidden knowledge that the network learned and reuse it in larger networks. You see these old slides demonstrated that that was possible. And so it was exciting to see that you could actually take the hidden representation it was never trained for and reapply it for something new. We could even interpret some of the hidden representations as acoustic phonetic features that linguists had discovered or postulated for many years before. And here we have a neural network that learns them automatically. So this was exciting. We played with two-dimensional neural networks, and lo and behold, you can do shift invariance in 2 dimensions, and then again, that's important for images. Now, in the 80s, working in neural networks was still very lonely. People called us neural nuts, like a cult. Some people said it's unscientific. Some said it's a wasteful detour with neural networks. Someone else said it's mathematically proven that only one hidden layer is enough. Of course, now we know that is not true. It's no better than K-nearest neighbor, but it's a wrong question. We can do it with LVQ, but again, all of this really dismissed the important features that I already described, namely that we can take multimodal representations and that we can learn hidden representations automatically, which is true to this day. Now, the only comment and complaint at the time that was true is that neural networks in the 80s required too much computation. So we were not able to really beat alternative approaches in the late 80s, and other learning methods that were simpler, like statistical methods, could get pretty much equal or similar performance. We always eked out a little, but it was not enough to take the community by storm. So it took another 10, 15 years and a lot more computation, a lot more data for these networks to be stacked in very much deeper architectures with many hidden layers, now known as deep learning, for this performance gap between other methods and the neural approaches to really show their power. And again, in 1910 and following, that became apparent eventually that speech recognition tasks in hybrid designs, for example, would experience a 30% improvement. Image tasks could be now recognized in much larger performance. And again, for machine translation and speech recognition, we reopened then again, the community reopened different ways of dealing with sequencing. And again, this was initially done by colleagues. Recurrent neural networks were actually also being explored already in the early 80s. We had an early paper in the early 90s on the recurrent neural networks for machine translation, but we couldn't get them to work because of lack of computation. And so it was reopened again in 2010 to 20 in that area. And as you all know, recurrent neural net encoder decoder structures showed first performance results. And again, with context vectors and eventually attention mechanisms, some of the limitations of long distance relationships could be overcome, and good performance was reached in actual practical machine translation tasks. Now, of course, with the arrival of transformers, and again, we'll hear more talks about that, they generalize or they advance much of what was learned from these previous methods, that with attention mechanisms and many layers, we can really get such powerful sequence-to-sequence modeling as a possibility that performance is just tremendous. And the hidden representations we develop are actually very powerful and advantageous. For machine translation, for example, we can see that it automatically, one of the algorithms, again, the algorithms in the late 90s and so forth, on statistical methods for machine translation and speech required algorithm like Viterbi alignment, where the alignment was was automatic, but still a single path. And here we see that, for example, alignments are automatically derived by attention vectors or attention weights that the network figures out by itself. So very exciting that these networks can basically remove some of the engineering design and give us such powerful improvements. So here you see, for example, results that we had. Every year we run a workshop on speech translation. It's the International Workshop on Spoken Language Translation. That is a satellite workshop of ACL. It happens every year, and we have a benchmark where interested groups can participate and try out their algorithms on a common task. And here you see the evaluation results over the years until 2019, these numbers. There's, of course, more newer numbers than that, but you see here very clearly the jump from statistical systems to neural systems, where a marked improvements was seen when the community figured out how neural translation is to be done. Very exciting, and again, it then reached performance levels that compete with human parity. And so we're today in a world where, given the right data and given the right task, we can actually achieve almost human performance on these tasks. Now, in speech recognition, similar thing was done. I remember still in the 1990s, 1993, a task was proposed by DARPA, which was the switchboard task. It was conversational telephone speech where people would talk about some random topic, and it was labeled and transcribed. And so that various participating groups would compete in trying to see how whether people can get accurate transcription of that conversational speech. And I still remember that the best, I think our team at Carnegie Mellon was among the best groups competing in one of these evaluations. And the best evaluation results were around 50% word error rate. Of course, terrible. Every second word was wrong. And that remained actually very persistent for many, many years. It was a very hard task, and high error rates were something that were difficult to overcome. Now, people tried, because it was a public benchmark, and many groups tried to improve results with both statistical approaches and eventually neural approaches. And it's clear to see from some of these curves that neural approaches there on speech recognition also wound up getting phenomenally better results on these. And as you see, for example, in 2013, there was a switch from Gaussian mixture modeling to neural networks. And then around 2017 in offline tasks, human parity was achieved. And then at our lab, we were eventually able to achieve human parity in 2020 at low latency. So for speech translation, of course, we need low latency. It has to do it quickly. And so we were able to beat that benchmark, beat human performance on this benchmark at low latency in 2020 with neural networks. Now that's, of course, very exciting. And here's the result on the latency. As you can see, with about a delay of 1 second, we can achieve a word error rate that's better than humans. That generated some news that was in the media and so on. So now what about these hidden representations? What are they good for? So again, performance is excellent with both at the speech level and at the machine translation level by now. But as I said before, this wonderful property that we can have hidden representation could be used in various ways other than just getting a good output performance. We can use potentially hidden performance in various ways to add information or to get zero-shot translation between languages that we hadn't trained for. And that again became possible in 2021. We published a paper, and Google published around the same time a paper on zero-shot translation. What do we mean by that? So we can build translators that translate from German to English and English to English, English to French. And if we do that all in one system and we share the neural representations, then we get for free combinations that we hadn't trained for. So we can get by zero shot a translation, let's say, for example, from German to French, even though we had not trained that particular language combination. So truly exciting, and this is work that we still continue because these hidden representations wind up giving us this power to explore a combination of languages, combinations of additional features, and so on. And so there is, of course, now also a lot of additional work. This is a picture from, I believe it's from a different group. It's from, I think, Liam, Holger Schwenk's group, if I'm not mistaken. They had an early demonstration of something that we had tinkered with all along, is where you say, well, if we have a representation of an object, for example, we can have a visual view of that, but we can also have a textual description. And as we see now, this is, of course, very powerful. That is true now in foundation models and in multimodal translation as well. So we can get, for example, a translation between text to image or from image to text. And again, through a shared representation, this is now possible. Now, with all these exciting technical advances, let me walk you through a few pictures of what we did with all of this over the time. And so these are images of systems that were developed in that context. This is our first speech translator in 1992, 91, 92, together with our partners in Japan at ATR. Again, it's a clunky system on workstations. It took minutes to compute. It could only handle 500 words. So it wasn't really practical, but was the first demonstration and generated a lot of interest. Along the way, we had Captain Kirk visit us at Carnegie Mellon because they wanted to know if the prediction or the hope that you see in Star Trek, that you have a universal translator, whether that might one day be possible. And I think we convinced Bill Shatner, the actor of Captain Kirk, in 1999, that this was actually possible and that we were working on this for the future. Now, again, 10 years later, finally, we had this engineered down so that we could build it so small that it would fit on a phone. And we started a company called Jibigo. As you see on the right, it came out with a device or a app that you could download on your phone. And indeed, it would translate then between several languages in real time for short sentences in arbitrary vocabulary, 40,000 word vocabulary, so that you could handle a conversation that's typical for a traveler. And we sold it. We had started a startup company with it, and it sold very, very well. Apple ran commercials with it and so forth. And eventually the company was acquired by Facebook, and Facebook used some of that technology then for building out language products at Facebook. Here's our team joining Mark Zuckerberg in 2013. Now, we use these kinds of systems also for humanitarian deployments. So after 2007 and 2009, we worked on various field deployments in Thailand and Cambodia and South America to provide healthcare providers with translation tools that are on iPads and so on, so that they can speak a sentence and translate it to someone speaking the other language and carry out a dialogue. We participated in an exercise called MEDCAP, Medical Civil Action Program, every year in Thailand between 2007 and 2013. And initially, it was very bad. People didn't like to use it. And at the end, it was good enough that people really liked using it for the dialogue between their patients and the healthcare provider, and even then used it in the evening to go to restaurants and so on. So we finally had reached a level of performance where people found it useful. And in hindsight, looking back, it was largely due to the success of the recognition and the translation, the power of it, but also on the interface. The interface was equally crucial because again, initially we had recognition and translation working, but if you don't have a suitable interface for people to work with it, it's all not useful in an actual practical environment. So the user interface is just as important as these technology by themselves. And as I keep explaining to practitioners, it is important to design the technology in such a way that it matches well with the interface, and design the interface so that it matches well with the technology. And that has many aspects to it. And I will say a few words on that as well. So here's in Cambodia, and recently in the European refugee crisis, we began on working on a project between Arabic and German. Arabic and German is not a very common language pair. There's a lot of data for Arabic English and English German data. So here we had a challenge of what do we do if the direct language pair Arabic German is not as data rich as the others? Can we share, for example, through common representations, a system that does better by combining these languages? And that's what we're actually doing now. There's, of course, also Ukrainian refugees now in Germany, so that our systems now support English, Arabic, German, and Ukrainian for these healthcare situations. We're collaborating there with a Institute for Seelische Gesundheit in Mannheim. It's a institute for effectively psychiatry, and it serves patients that are traumatized by war experiences. And again, you see here our staff working on using these devices to communicate with patients, between the doctors and healthcare providers and the patients in those languages. Now, the next thing we also did was the question of how do you deploy this now in a lecture scenario? Now, a lecture scenario is different from this dialogue scenario that I explained. Why? Well, in a dialogue situations, again, the interface is very crucial. In a dialogue situation, it has to be mobile, it has to be fieldable, it has to go back and forth between the two speakers. So the interventions are usually not very long. You have a sentence or two, and then the other person responds. And but it has to be fast, and has to be small, and has to run on a mobile device, and so on. In a case of a lecture, it's very different. You have a continuing monologue. You have large vocabularies. The speaker never stops speaking. It just continues on. So you need to somehow, you cannot wait until the end of the sentence. You have to produce output as fast as you can. So doing this in low latency was a real crucial element, and doing this quickly, and inserting periods, for example, periods and commas. The speakers don't say periods and commas, but we need to worry about the readability of the text. So inserting periods and commas is an essential element of that. We have to eliminate hesitations, coughs, and ums, and so forth. So doing this all in real time very quickly, so that you get readable text, so that students, for example, in a lecture can follow a lecture in real time as the lecture goes on, was a key challenge. We had a first demo in 2005, but a first working version at the university in 2012, where we actually deployed it at Karlsruhe Institute of Technology for all the students in Germany, so that they could, for example, foreign students can listen to a lecture in German and vice versa. So the key requirements are: it has to be simultaneous in parallel to the speech. It has to be low latency. So we have a few papers that were at the time publications on low latency speech translation, which initially was not viewed as a problem until people realized it's really crucial. How do you do low latency speech translation? Because very often you have to output a word without having the full context of the sentence, because of the time pressure to deliver it quickly. And doing word reordering, for example, in machine translation, or to output the words as they come, and output the translated text on the other side, when you have not even seen the ending of the sentence, is in fact one of those AI challenges because it has to be predictive to do this. It has to be also domain unlimited. And again, we have spontaneous speech and continuing speech. So this was first demonstrated in 2005. As I said, we gave a press conference in Germany and then Carnegie Mellon to show that this is even possible. And then through various projects, we extended this to university use in 2012 in Karlsruhe for actual students. And we also worked on a project in Europe on deploying it to all the European languages for use by European agencies. In this case, of course, it has to be fast, large vocabulary, but it doesn't have to be. It doesn't necessarily have to be offline. It doesn't have to be on a mobile device. You can run this on a server very well and very nicely, and so most of this was then done server-based. Can you guys still hear me? Can someone respond?
Yes, it's possible. It's possible.
Oh,
There
okay, thank you very much.
a brief break only, so it's fine.
What is that?
There was just a brief pause, but now you are hearable again.
Yeah, there is a thunderstorm here in Singapore. So if I lose you, please let me know or send me a text message on my phone.
Okay.
In these projects, of course, we were always evaluation-based. We can do ASR and MT and measure the blue scores. But as I said, also the deployment in a suitable interface was key. Otherwise, for example, we would never have recognized the importance of low latency. And so here you see this device as it runs at the University of Karlsruhe, or KIT now, since 2012 for foreign students. The press reported on this, and then we got a lot of interest again by the European Parliament, and then made many deployments in the European Parliament where they do have human interpreters that are very good. But again, there are situations where they find it stressful or boring, and they welcome an automatic system that they can deploy in certain instances. So this is the Rectors Conference at the European Parliament, and we developed a very good relationship there with the practitioners in the field. Here you see the Secretary General of the European Parliament. And again, we did field tests showing that this is actually feasible, but that it also works in synergy with human interpreters, so that it's not about replacing your human interpreters, but complementing their efforts. And that's, I think, the big success or big insight there. Now, in order to deliver it to the Parliament, we also had another startup company called Kites, and the pandemic happened. And during the pandemic, everybody went online, and Zoom was an overnight success to deliver lectures everywhere. And so Zoom noticed what we're doing with automatic transcript and translation and acquired the company, Kites. And so if in this Zoom call, for example, you turn on subtitles, you can do that here in this Zoom call if you wish. Then it will automatically transcribe the speech of the lecturer and also translate it into another language. And this was the result of this company Kites, which was acquired by Zoom in 2021. So over 2 years now, Kites, or the team, together with new colleagues at Zoom, have now developed this transcription and translation capability in Zoom calls for 30 languages and translation back and forth. We are quite excited to see that that's possible. You see here in the Zoom call, there's something called AI Companion. It now not only takes the transcript and the translation back and forth between what people are saying, but it can now also do chaptering and summarization of a lecture and so on. So it's a wonderful new, exciting way of using AI in practical ways when we have meetings between people. And you all have seen this, so I don't need to really demonstrate. Hallo, meine sehr verehrten Damen und Herren. Es ist mir eine große Freude, dass ich heute bei Ihnen sein darf und Ihnen ein wenig über unsere Forschung zu erzählen. Wie Sie wissen, arbeiten wir schon seit sehr vielen Jahren an dem Problem der Übersetzung gesprochener Sprache. So this is just the standard Zoom product now that you have here in the Zoom call, and as you can see, it generates here subtitles and also translations in multiple languages. Hello, so where are we? So if this all is now already possible and is already deployed in practical products, what do we still have left to do? Well, fortunately or unfortunately, whichever way you want to look at it, there's still many challenges remaining. In our case, we're working very heavily, for example, on noise and crosstalk. These kinds of systems don't work very well when you go into very noisy restaurants or bars, for example. Then they are still suboptimal. We still can't handle all the languages of the world, 7,000 languages. When people mix two different languages, it's very problematic. If people, for example, would say in German, downgeloaded or webgecasted and so forth, mixing English words into the German language and then adding the suffixes to it, that confuses recognizers and translators. So that's a subject of current research that we're doing. Accent and dialects is still a very open, big issue. We're humorously working on Schwäbisch, which is a local dialect in Baden-Württemberg in Germany. But of course, dialects are everywhere. In the Arabic world, it's a huge problem where accents and local dialects really make the language quite different from modern standard Arabic. And again, the big problem here is there's insufficient data. And so building a system is challenged by the fact that we don't have enough data to train a separate system. And are there separate ways or different ways to deal with it, to do this? And we believe there is. And so this is, again, exciting work that we're happy to do and interested in doing. Context is needed to handle, for example, names, technical terms, acronyms. These products don't work very well if you're speaking a name or an acronym that is unknown to the large system. That is generally true for modern AI systems. And how to do that is, again, an issue. Meta information, how do you remove bias? How do you talk appropriately given gender, emotion, politeness, rudeness, style, formality, and so on? All of this contributes in the way things should properly be translated. And the systems currently are still too bland to be really successful at that. And then doing summarization. Now, what is also missing is, and I want to do that here for the rest of my lecture here, is to also talk about the next generation that we now working at our lab, which involves automatic dubbing, voice conversion, lip translation. Now, what do we mean by that? Well, this is on large. Okay. One word on large language models, since everyone's talking about it. Large language models are amazing, of course, because we can now, in an unsupervised way, again, thanks to the power of neural networks to develop hidden representations, we can actually do predictions in ways on things that haven't been pre-formulated. And so large language models, as you know, can do translation to some extent and so on, but they're still not at the level yet where they can fully replace these translation or speech systems because they're slower, they are not low latency, they're expensive to run, and so on and so forth. So not quite there yet, but it's again in a very exciting direction that we're also watching and observing. Now, multimodality, again, communication is not only text, as I said, we have speech. So we have, for example, multimodal input. We, for example, as humans, we read lips, we use handwriting, we can use images. We can also use what people are pointing to, pointing gestures. If, oops, what happened? You see these slides, right? Tracking focus of attention?
Yes, we see them.
Okay. So here, for example, in open meeting, you not only need to know what the person said, but you need to know who the person says something to. Or if you, for example, have a pointing gesture, you need to know who the person is talking to, right? What is the person saying with respect to a pointing gesture? So these problems become automatically multimodal because you need to now interpret a visual cue that gets combined with the acoustic cue. And those are issues that we're continuing to work on in the direction of language transparency or language transparent meetings. If you're in a meeting that is hybrid, now not only over video conferencing, but in a open environment where you have the speaker sitting in the same room with people, suddenly these things become very important. Identifying who is speaking, who is someone speaking to, what are they pointing to, and so on. So these require noise issues, they require pointing gestures, they require facial direction, and they require a number of visual input and output cues. For example, we worked here on translation goggles so that you could sit in a meeting and have the translation in your goggles, or directional audio, road sign translation, and emotional speech, for example. You know, depending on how you speak something. Oops. Sorry.
Go to sleep now. Go to sleep now. Go to sleep now. Go to sleep now.
So all of these things then generate different emotions, and translating it correctly needs to include emotion. So we get to language transparency, and again, the final point that I'd like to walk you through is then also the language transparent output. Let's say you at the output, very often we get asked if you get subtitles in text, that's wonderful, but could you give us, for example, voice output? We have traditionally resisted this because in a lecture hall, it's impractical to give everybody headphones, and or if you have a speaker, it's noisy. So and then the other problem is when you speak something out, you cannot revise it or change it anymore if the translation turns out to be wrong. And so text has many advantages in a monologue or in a lecture translation. However, in many other situations, having dubbing, having an automatic voice is nice. Like, for example, movies, when you want to have a dubbed movie in another language, then real-time performance is not necessarily important. And you may want to do this as a service, a dubbed service, to create automatic face dubbing. Now, traditionally, this is done by having a human actor speak the translation in the other language and in such a way that it fits the video. So the actor has to speak the translated sentences more or less in the same way that the lips of the original video are moving. Now, we didn't want to do this, and we said, well, let's look at another way of doing this. We take a video, we do speech recognition, machine translation as before, and now we do...
Professor, can you please select the corresponding slide? We can't see the slide. We see all the slide together, but not the corresponding slide.
You see all the slides together. Okay, let me try to reshare the... Do you see this?
Thank you. Yes, okay. Thank you.
Sorry, was this a problem all along or just now?
Maybe for 2 minutes.
Oh, I see. I'm sorry.
Thank you.
So what we have here is a so-called face dubber. So we take the video input, we have this recognition machine translation, and then we can, of course, synthesize the text in the output. But if you synthesize the text in the output, it doesn't sound like you anymore. And of course, it doesn't match the lips from the video on the input. So what we do is we do a voice conversion, take the output translation, the synthesis of the output translation, and we first convert it back into the voice of the original speaker. So in this case, if it's me, we convert it into my voice, even though it's Japanese or English or German, whichever. And then we modify by basically deep fakes. We modify the video of the image so that the lips move in synchrony with the synthetic output that we had just generated. And this is an idea that we actually, for the first time, tried in 1999. And I have an old video where a student of mine tried that. It didn't look very good. It looked spooky as people, or creepy. People said it looked creepy because the lips are very artificial. But now with modern neural networks, we can do actually a fairly good job that makes it look much, much more natural. And I want to show you that in an actual lecture setting. So this is the original German piece from my...
ただまた認知システムの公認にな
Sorry, this was somehow wrong.
Super, then I warmly welcome you again.
Super, dann begrüße ich Sie ganz herzlich wieder zu unserer Vorlesung Kognitive Systeme. Wir fangen heute ja mit dem tatsächlichen Stoff an. Ich bitte zunächst mal die paar Minuten. So this was the original German lecture. We do this entire process, as I said, and we create an automatic dubbed version of that piece in English.
And to our lecture on cognitive systems. We are starting today with the actual substance. I would like to apologize for the delay of a few minutes. We still fought with the technique here because the microphones are...
And you say, of course, well, Alex Waibel speaks English. This is sort of a trick. Now let's do Japanese.
皆さんをお招きします。今日から実際の実態から始めます。数分遅れて申し訳ありません。マイクがハミング音で埋め尽くされているので、まだこのテクニックで。
Okay, and so that you are convinced that we're not only doing this for my face, we can do it with the president of the Carnegie Mellon.
21, a Smart City Institute, which has become a campus-wide initiative that encompasses so much of our work at the...
So this is the original video of our president at Carnegie Mellon. And he does not speak German, he does not speak English, but here through face dubbing, we can do that.
21, a Smart City Institute.
Sorry.
21. Ein Smart City Institute, das zu einer Campus-wide Initiative geworden ist, die so viel unserer Arbeit an der Schnittstelle von Technologie und Gesellschaft heute umfasst, ist eine Feier einer harten Arbeit von zahllosen Individuen.
And here in Japanese.
21. スマートシティ研究所はキャンパス、ホワイト、イニシアチブとなりテクノロジーと社会の交差点における我々の仕事の多くを網羅しています。
Okay. So you see how we can
21.
we can do this also with the German president, etc. But you get the idea. Okay. So so this is of course for communication across languages. Maybe a little bit crazy application we also did in 2021 on a deep dive to the Titanic. Underwater, you have the same problem that in transmission in salt water is not possible. So we actually did the same video transmission by doing speech recognition, then transmit via sonar signals from a submarine to the surface. Then we do speech synthesis, voice conversion, and again, neural lip conversion in an actual deep dive on a submarine. So again, it's a different application. Maybe it's a shift from language translation, but it's a low bandwidth type of communication example where these same technologies can now be applied for very dramatically different applications. And this is something that we did on a mission, actually on a dive on a submarine. You all heard last year about the submarine that got lost in the Atlantic where people died. That I was probably one of the few dives before that on the same kind of submarine. So here these were pictures from this dive and the submarine. Here's us in the submarine doing the speech experiment. This is our student from Karlsruhe to do it at the surface to resynthesize the video in the output. And I'll play you the video of how that then came out.
Hello, I am Stockton Rush, CEO of Ocean Gate. On our research mission, we are planning a deep dive to the legendary wreck of the Titanic.
I am Alex Waibel. We are excited to be part of this mission. Our role is to contribute to better communication between the submarine and the ship on the surface. Such communication is crucial. Unfortunately, normal radio transmission does not work deep under the sea. That is why we are planning to try a different approach. We are recognizing speech in the sub, and we transmit text via sonar signals to the surface. Finally, we resynthesize ellipse synchronous rendering off the video and speech off the speaker.
All right. So here are final pictures. So let me conclude. I'm out of time. So I hope I can convince you that we're not finished with all these problems yet, because the goal is ultimately not just to do translation of text, but to bring us closer as human beings in all kinds of different situations. Language transparence, as we call that. That requires overcoming language problems, but also interface problems. And the technology is a key feature in these applications, but also the interface to bring this closer and bring it naturally into the communication process between people. All right, thank you very much.